we're trying to do the H-coordinate theorem. Okay, so we have a n-dimensional cobordism, and 0 and 1. And it's an H-cobordism, so the inclusions from either end are homototal equivalences. Okay, and it's simply connected, so phi 1 of x. And I'm gonna I think I want to focus on, if necessary, to make things easy, I'll focus on the case where, I mean, the theorem is true in general, but I'll focus on the case where all the homology, I'm not sure when I might need this, but all the homology vanishes completely. So the homology of the ends. Well, the ends are compact, so I'm just saying use homology. So here. Which, like, then, you know, by this theorem are actually homototal sphere, whatever. This is just, I'm not sure whether it is, but that might make our proof easier to think about in some case. And then the goal is to prove that then, prove that x is actually diffeomorphic to 0, 1 crossing. And the way we're going to do it is pick a Morse function, so prove f from x to 0, 1, and cancel over equals. Okay. And in order to cancel our critical points, we want to think about flow lines between from critical points to critical points, and we also need a gradient like vector field. And that gives us handles. And that gives us handles. And so we'll just go back and forth between the Morse function, the handles, and so on. Okay? And maybe I didn't say this, let's assume it's index ordered, so that all lower index critical points are below higher index critical points. And then step 1 was going to be trade 1 handles for 3 handles. And I forgot to mention dimension constraints. The theorem is certainly true for n. The certain theorem is true for n large enough. How about we try to do it this way? N greater than capital N, and let's figure out what capital N has to be as we go along. Okay, I believe this works for n capital N equals 6. Okay, let's keep track of. Let's try to keep track of where we use large dimensions as we go. And it may be that there's subtleties in 6 that are worked around in some weird way, and so really I'll just root for 7 or something like that. Let's see. So the trading 1 handles for 3 handles story, which we started on, was to you know, the 1 and 2 handles gave us a presentation of the trivial group. X, it's trivial, and so we know that we can reduce to the trivial presentation, or a trivial presentation of the trivial group. Trivial presentation, which just means one generator and a bunch of generators, and each generator is the identity. It's declared to be the identity by its relation. The trivial presentation using these moves. And so what do we need to do? We needed to, well, first of all, we were going to use handle slides. Right, that was, I mean, I'm just going to tell you so far we discussed using handle slides is just taking one relation and concatenating it with another relation, okay? So that's relation I goes to relation I to relation J. Actually, I didn't mention it, but J really has to be different than I, okay? So if you want even to get Ri squared out of Ri, you have to make a copy of Ri first, which I'll talk about also. So that's I not J, and that's a handle slide. And then, so that was one of the things we might use. And the other thing we might use is remembering making copies of relations, which actually you can think of as just creating the relation 1, and then doing this. So if I want to make a copy of Ri, first I introduce the relation 1, and then I do this one to 1, and I get 2 copies of Ri. Does that make sense? And but this was achieved geometrically by introducing 2-3 pairs. So anytime you introduce a canceling 2-3 pair, the index 2, the descending circle for the 2 handle just runs around is a circle that bounds a disk, first of all, so it just reads off 1, and then you slide it over something and it reads off whatever you have. Okay? So this is where the why we get 3 handles in this process. Okay? And we can't avoid that, it seems like, depending on the Curtis conjecture. So now the last thing is, so suppose we've done this, but we have the one other thing is doing things in the form generator GI, generator GI inverse goes to the identity, right? So let's suppose we've done we've gotten down to a presentation of the form. Every relation is a string, can be reduced to the identity just using these moves. Okay, and so suppose we already talked about how. So we know we can do this. So we get this is going to be finger movement, but I want to talk about it today. So this is what I'm focusing on. Suppose so let's call this active. Handle slides and 2 pairs. Every relation Ri reduces R reduces to 1 using GI inverse goes to 1. Right? Just repeatedly using that process. So that means, we sort of got this nest of canceling generators and their inverses. We start somewhere, we cancel them, and then we get another pair that we cancel. So what I want to do is show geometrically what's happening here and why we can geometrically eliminate such a thing. No, it's not supposed to go down to, not reduce to 1, I'm sorry. We don't want our relations to reduce to 1. We want our relations to reduce to a single generator, right? So each R is going to reduce to some, to R equals some G for a single generator. Well, I should say that for one generator, or it might reduce to, or R equals 1. Okay, that could be enough. We could because of the fact that we introduced a bunch of 1s and then slid them over, presumably we have way more relations than generators, and so in the end, after all this process, we should get a bunch of, each generator has a relation with it, and then all the other generators are just 1. All of the other relations are just 1. So what does this mean? This means that the attaching S1 for the 2 handle, HI, well, where is that attaching S1? It's in the boundary of the 0 handle. There's no 0 handle at all, because we've got a non-empty from 0. There's no 0 handle, and then I've got a bunch of 1 handles, right? So this is in the attaching S1, which is in 0, 1, cross, and 0, union a bunch of 1 handles. So how does that attaching S1 read off a word? It reads, it reads off some word, and as we go around, the way we get the words, we just write down the word we write down the name of the generator corresponding to the handle every time we go over a handle, which means every time we intersect the ascending sphere for the one handle. Does that make sense? You understand what I'm saying? So I've got, I've got a 0, got 0, 1, and then I've got a one handle here, and then I look at that. So this goes over here. Then I read out if this is handle HI, then I read out this direction, then I read out GI. Okay? And so what this means is I go along, and then here's the attaching sphere, right? So the attaching sphere, handle H. I don't want to call this handle for the two handle H. Okay, that my indices currently are referencing the one handles. Okay, for the two handle H, reads off the word sort of by intersecting the ascending spheres for the one handles. So I run around, I read out, and so now what this means, if I see GIG inverse, then I'm supposed to, so the point is, can I actually, the question is, can I do this geometrically? And so I see GIG inverse, and then it comes around, and then it goes back over. Now you might think, great, okay, no problem, I can do that. But in order to pull this back over, what do I need? I need this to bound the disk. I need this loop to bound the disk inside the boundary of 0, 1. This is
so what is that? Yeah, what is that 0, 1 cross?
It's the boundary of. I mean, I start. The two handles are. I'm only looking at the one of the two handles. I've got M0, thicken it up a little bit. That's the point. It's just you always thicken up a little bit before you attach anything in order to actually be the right dimension. So I thicken it up a little bit, attach the one handles. So now the question is, how do I know that? So I've got this little loop here. It doesn't hit any other one handles. How do I know it bounds disk? So I've got the loop that starts on this on this ascending sphere, the belt sphere for that one handle, then goes around somewhere and comes back.
It's not clear that it doesn't bound like a punctured torus or something like that.
Well, so
what if there's like a
we need
foot
to use
or
pi
something?
1 equals 0 now. Okay, so the first thing is so I can think, so I get out of this, and we call this loop gamma. Right? So I get this loop gamma, which it comes down the same side, so I can actually push it down into M0. Okay, so I get loop gamma, which is really in, where is it exactly? It's in M0 minus the attaching spheres for the attaching spheres to the one handles, which are a bunch of points, right? So minus some points, right? Because it doesn't, I've got this, I can push, it starts here, goes up, goes around, comes back, which I might as well say it starts here, goes across, and goes back, right? Okay, and now it doesn't go over any other one handles, but the point is I want the disk to actually, I want to pull this disk back, not go over any one handles, stay in the complement of the attaching circle for the one handle. So there may be a one handle here, for example, right? Or there may be even, well, okay, I'm going to give you what's a misleading picture, show you what you might worry about. There might be something like that, right? Well, this is where the dimension is going to help. One place where the dimension is going to help, right? If the dimension of M0 is big enough, in particular bigger than 3, and bigger than 2 in this case, right? Then, so if n minus 1 is bigger than 3, then pi 1 of M0 minus some points equals pi 1 of M0. Removing points from a 3 manifold or higher does not change the fundamental. Removing points from a 2 manifold does. Okay? So, therefore, because pi 1 of M0 is trivial, gamma bounds a mapped-in disk in M0 minus some points. Now, a mapped-in disk in a 3 manifold might not be embedded. A mapped-in disk in a 4 manifold might not be embedded, but a mapped-in disk in a 5 manifold is embedded. So if n minus, so my board working,
Right.
order is getting kind of bad, but the next thing is, if n minus 1 is greater than or equal to 5, gamma bounds and embedded this.
It's like a perturbation argument.
Right, so I'll tell you that in just a second, in 0 minus points. And so, well, if you buy, I'll explain that a little more carefully, but if you buy that, then you can do the finger loop. You can pull, therefore, can eliminate both intersection points. That's a really one of the units, both intersection points. You want to eliminate this one. So what's the, it's a transversality argument, okay? The rules for counting dimensions of transverse intersections are the same when you're talking about a something being transverse to itself, okay? And so if two surfaces in a 5 manifold are transverse, they're disjoint because their codimensions add, right? And so so does that make sense? So far we need capital N equals 6. Okay.
That's still 5, right?
No, that's N minus 1.
Greater than.
Oh,
Because
okay.
that's the level set.
Right.
So this is maybe everything's 5 here. So therefore we can, the conclusion of all of that is that then you keep iterating the process, right? And you eventually get down to where each two handle either doesn't go over any one handles or goes over a single one handle once, right? Each two handle either cancels a one handle or doesn't go over any one handles. And each one handle, of course, is cancelled by a two handle. Now, of course, you might say, what if two handles cancel the same one handle? But then you can slide one off the other. Just sort of, that's a simple. If I have one handle here and I have a two handle going over there and another two handle going over here, and I do a little slide, there's the intersection with this, and it's fair to do a slide like that. And the two handle comes off, the other two handle comes off. So therefore we can pair off the two handles to cancel the one handle, therefore we can cancel all one handles. We may have lots of extra two handles left over, of course, that's not, well, that's the next goal is to cancel those. But the one handle, there's sort of we do this a little bit, you'll see the argument for the higher dimensional handles is a little different. Well, in particular, we don't have to use the fundamental group quite. Fundamental groups are. Any questions? Yeah, go ahead.
I just want to make sure I understand. So
Yeah.
the reason, so if you start with some one handle and you want to argue I can cancel it, well, that's like some guy in pi 1.
That's right.
And so now you have this word that you write down, and this argument says that I can get it down to where it just goes over some two handles.
Well, okay, so that
And
one
that's how you
handle is
cancel it.
one of many generators.
Right.
And then I have all these complicated relations.
Okay. Oh, I see, but that's why you
and
want
then
all the
I
relations.
do all those relations, right? Eventually, the first step I would do is do the handle slides and the copies, right? Until every relation eventually becomes
Just some generator.
just some, well, algebraically it looks like some generator, except that as a word I may still see a bunch of GI inverses, right? And then I have to geometrically cancel those, not just algebraically cancel those, and that's what this
So
argument
after
is.
that,
After that
all
geometric
the
cancellation,
generators
then right, the relations are just this generator equals 1 or no relation at all. Make sense? So, now we move on to the. And as I mentioned before, should we want it, we can do the same. Let's do a quick. We want to make sure that putting 3 handles in. I may or may not care about this, but if we wanted to also do the top dimensional handles, right, which would be n-1 handles, I'd want to make sure, I'd do the same argument, but I want to make sure n-1 is not, I want to ensure that n-1 is not equal to 3, right? In other words, if I could flip it upside down and get rid of the top dimensional, the n-1 handles, unless n-1 is equal to 3. And so I want to make sure that n-1 is bigger than 3, which means n is bigger than 4, so that's fine. It doesn't add anything. We already are in that situation. Okay. So the next step is we want to cancel the rest of the handles. And the first thing we do is just algebraic preparation. So algebraic preparation. Okay, so there's no, yeah, actually, but let me, I realize I really do want this. So because of this, can also cancel all n-1. Now the advantage to all of that is going to be, I've got no one handle or n-1 handles, and that means that all level sets now are simply connected. Okay, so the conclusion of this is, all level sets, anywhere where anything is being attached, are simply connected. See, initially, the two handles were not being attached along simply connected level set. The two handles were being attached above the one handles. And similarly, the level set, if I have n-1 handles, then the level set just below them is not simply connected, right? Because flipped upside down, that's just the same thing. That's a level set above one handles. So that's why I want to get rid of those extremal indices. And so once you have that, then the only way you get certainly all, here's the reason I'm hemming and hawing right now is you can get, if you have a 4 manifold, right, you can get non-simply connected level sets with just 2 handles because you can change the fundamental group of 3 manifold by doing surgery on it. Okay, you can, so let's actually think about this. Let me leave a question mark here, make sure I come back to that. Right, because we know that if you take a 3 manifold and remove a solid torus, say the 3 manifold is say S3, and you remove a solid torus, you can then glue it back in a way to get S1 cross S2, for example, which is not simply connected. So even though you didn't attach a 1 handle to the 4 manifold, you didn't take a 4 ball and attach a 1 handle to it to get something non-simply connected, you still ended up with a non-simply connected level set. But if you, so what one needs to think about is in what dimensions does that happen in general? In what dimension does a certain surgery make this level set simply connected? I think, but I want to come back to it. I think that we're still fine because of our dimension constraints, but let's, when we come back, let's see what we need. So the algebraic preparation to cancel the remaining 1 handles is to think about so we look at the Morse chain complex, C star. What is it precisely? I've got, so the Morse chain complex is, well, 0 goes to, well, in this case, I've gotten rid of n-1, so we'll just put another Cn-1 equals 0 and letting n-1 handles. And then that goes to Cn-2, dot, 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 Cn-3, dot, 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 C2, C1 is 0, 0. Now I didn't talk before about a Morse chain complex on cobordism, but you can do the same thing, and you can actually say, what's the homology of that Morse chain complex? Of course, the bottom and the top may have non-trivial homology, as, you know, the bottom level, and this is not gonna see that at all, right? So can anyone guess what normal algebraic topology, homology you're getting when you take homology in this chain complex? So I've got some mystery manifold at the bottom, then I attach handles to it. And then I just compute the chain complex that only sees those handles.
Sounds like excision or something?
It's actually just the relative homology. So, which is related to excision. But it's, I mean, yeah, there's something in there. But what we get, the homology of this, is precisely, I mean, so what you have is you have a sort of a cell, you can think of, I could have put a cell decomposition somehow, CW complex structure on the bottom level, and then the handles give me more cells. Okay? And so then I've got a relative cellular homology, in which I'm just computing, but I don't really, the point of relative homology is I just ignore the homology of the thing I'm doing relative to. I'm saying that very clearly, but anyway, you know what I'm saying. The homology H star of this is equal to H star of X rel and 0. If you do the homology going the other way, you have the homology rel at top. Because you're just thinking of these things as cells attached down. So for example, if I have a, I attach a 2 handle to M0, right, then I create a relative, even if the 2 handle goes around some non-trivial, I mean the attaching circle for the 2 handle goes around a non-trivial loop at the bottom, I'm sort of basically just that's still a relative cycle, because this boundary lies in this subspace. Okay, so relative homology is generated by relative cycles. Relative cycles are things whose boundary is not 0, but whose boundary is in the subspace. Okay, and then if there's a 3 handle, for example, that fills in that hole that I created, then that 3 handle, the boundary of it equals that 2 handle, so that relative cycle is relatively homologous to 0. Okay, that's the picture. So you can see this pretty carefully, but in particular, this is 0 because of the inclusion M0 into X is homologic equivalence. Therefore, this chain complex is what's called acyclic. C star. I mean, this is just a definition of what. If you've never seen the word, an acyclic chain complex is a chain complex whose homology is all 0. Okay. And there's a nice thing about acyclic chain complexes, which is that you can split them up in a very simple way. You may have seen this in my mind. You can always find a so therefore it splits. C star splits in the following way. I'll write in this case exactly. I'm just going to ignore Cn minus 1. I got 0, and then I basically have the image of the boundary map plus so the image of the boundary map plus some sort of complement. C n minus 2 prime, and then that's going to map to the image of the boundary map, direct some complement C n minus 3 prime, and the point is that this map is such that the image, we already know the image goes to the kernel there, with C n minus 2, that map is an isomorphism. This map's isomorphically onto the image. Well, that's sort of obvious, and then this maps all the way down to the image of the boundary map when we get image of the boundary map from C3 to C2, direct some C2 prime, and so what am I saying? I'm saying that you can, in general, we know that the image, because the homology is trivial, we know the image equals the kernel at each step, right? And the issue is, can you find some complementary, sort of orthogonal complement, which projects isomorphically onto the image of the next stage, right? We know that the whole thing projects onto the image, and so it's really, we know that the image of this stage is isomorphic to this whole thing mod this thing, because that's the kernel, right? And so we need to find some complement that actually realizes that. And of course, over field, that's easy. That's just linear algebra. You're just finding orthogonal, taking orthogonal complement from the stage. But over Z, it's a little more subtle, but it's not really that hard. Okay, and all it's really saying is, in this case, the image of the boundary map is actually 0. Right? So the first step, maybe I'm just, maybe more complicated than it seems, but the first step, this is 0, and this is the whole thing, right? Because the image is 0. But it's the next step where it gets in, and so then I've got the image, and now the real point is that there's sort of a simple algebra, which I won't prove, which says that, so this follows from following back. If you have a map from Z to N to Z to N, if I have a homomorphism from Z, these are all, it's critical that these things are all free abelian, right? Such that Z to the N mod, let's call this a boundary map, mod the image in the boundary map, is free. That's what I want to say. Then in general, the image could be something, so I get torsion, right? But if I get a free group a free abelian group when I take, then what I want to say is, then there exists a subgroup H M. Free is free. So any subgroup of free abelian group is free. Okay, but such that Z to the M equals the image of boundary map plus H. So in general, if you take Z and you have 2Z inside it, right? That doesn't happen. You don't have a complement. You don't have an orthogonal complement to 2Z inside Z. And so once you do that, you can figure this all out. So the whole point is you're just going to split up each, and then each at every stage you just have an isomorphism from here to here, right? And so we're really thinking about handles all along. Okay. So at each step, the prime part are going to be the things that cancel the image part. Okay, we're going to have an isomorphism from Cn minus 2 prime to the image of the boundary n minus 2, right? So we're gonna find a basis for this set of generators for this free abelian group here, and then take the image of it here, right? And that'll turn this into the identity map, right? And then as the identity map, if we can sort of realize that geometrically, then that means we've got a generator here canceling a generator here, and then keep going a generator, and then these will be missed completely, right? And so they will. So these things will be cycles, right? In the kernel of following that, but they're all canceled by these. These will be cycles, and these will be ignored by homology, but they'll be killing the next thing. So
what happens at the end?
Oh, at the very end, this stuff all goes to 0. Okay. And well, no, this stuff all goes to 0, and it's killed. Right. At the very end, this maps isomorphically onto 0. Therefore, it's actually equal to 0 in this case, just like this one was equal to 0. Okay. At the very end, there, what this is really saying is that the image of the boundary map from boundary 3 to the second chain group is the whole thing. Boundary 3 is trajected.
I'm sorry, why is it saying that?
Well, because if you believe this theorem, right, then C2 prime maps onto the image of this map isomorphically, but this map is the 0 map. It's just saying every 2 cell. This is sort of easier. I mean, if there's no H2, right, then every okay, so I need to know that the boundary map, every index 2 critical point, maps to 0 because there's no one handles at all. Okay, so it doesn't, the C1 is equal to 0. So every generator of C2 goes to 0. Therefore, H2 is generated by all the index 2 critical points. Okay? But it's 0, therefore every index 2 critical point is in the image of boundary 3. So therefore, this boundary 3 is the entire C2, and so this has to be 0. It doesn't have this. I have a feeling I'm not saying.
So you're saying if you have a 2 cell in this thing that does not have a boundary 1 cell, then it must be the boundary of some 3 cell.
I'm saying every 2 cell, no 2 cells have a boundary 1 cell because there are no 1
Right.
cells.
Right.
So then,
Therefore,
yes,
it has to be
yes,
the boundary
exactly.
of some 3
Yes,
cells.
exactly. Because the homology is true.
Okay, otherwise it would be untrivial.
That's right.
So say a 3 cell, for instance, or a 3 handle.
Yeah,
It can either cancel with a 2 handle or a 4 handle.
exactly.
And so we've split
Right.
this,
Right.
through the
Which
ones
ones?
that cancel,
Right.
2s and the ones that cancel.
Exactly. We split every
Paired them all
bunch
up.
of, except this is purely algebraic.
Yeah, just algebraic.
Algebraically, we sort of found, then these are free, so they have generators, right? And so now we found these, so another way to say it is, there exists basis for each of these free abelian groups, with respect to which so therefore, there exists a basis, bases for each CI with respect to which all boundary maps are in the form, what's the best way to say it? I want to think of, I want to say I. So something, this is the boundary of this, the columns correspond to things in the domain, right? Is that right? Yes. Columns correspond to things in the domain, right? Rows correspond to things in the range. And this is saying, so these first basis elements in the domain, their boundaries of the identity here, right? And then the other things go to 0. Maybe put the I somewhere else, but you get the point. Okay, maybe the I should to have a consistent way to break them all up. Maybe the I should be in one of the off diagonal blocks.
Sort of as what
That's exactly. I mean, this is just an algebraic way of saying what
Eric is saying.
But really, I should have said linear combinations of handles, right?
Right. Really, it's linear combinations of handles. So there exist these bases are linear combinations of handles which themselves generate things. Okay. But now we need to say that this is just a different basis for z to the n, right? And so we can change one basis into another by elementary row and column operations. Okay. Well, by just adding one, there exists. So each basis is a linear. Each basis element is a linear combination of the original basis elements, right? So there exists a. So we can get to the new basis, these new bases, by adding multiples of one basis element to another. Right?
So these are all just handle slides.
Exactly. So this is handle slides. The upshot of all of that is that by using handle slides, well, okay, so suppose I see an algebraic handle slide I want to do. And I want to add this basis element to that. Well, then I just have to choose. I have a descending sphere for this and a descending sphere for that. I pick some arc along and I do the handle slide. Okay? Now, there's lots of different choices there, but you just do one. Okay? And so, all handles are paired off, you're algebraically canceling pairs.
But are they actually canceling?
Now so now what does it mean to be algebraically canceling? It means that there's algebraically one flow line from this critical point to that critical point. But there might be lots more that cancel that we have appear with opposite sign. And there also might be zillions of flow lines between this critical point and all kinds of other critical points, but they all pair off algebraically. So then we have to geometrically cancel, okay? So now we need to, now I'm not interested in order to algebraically, I want to get to the point where they are geometrically canceling pairs, which means a single, exactly one flow line from that critical point to another and no others. But in order to do that, I first need to geometrically cancel the pairs of flow lines that appear with opposite sign. Geometrically cancel pairs of flow lines with opposite sign.
We've done something like that before. I'm not sure if that.
Well, this is very similar to what we did in the bottom right corner with the one handles. We had two things. We had two points where we had something go over a one handle and then around and come back, right? And now we had to pull it back. We had to argue a disk existed. But it's a little bit more subtle here because we don't just have a loop that's going over, right? So we have to think, where our loop is going to come from, and it's we use the fundamental group trivial to do this.
So I guess, what do you mean by cancel a flow line? Do you mean like modify?
What I mean is modify. Right. This is going to be a finger move. What I mean is modify the move the attaching spheres by an isotopy, so as to eliminate a pair of intersection points. So we focus on this. So it boils down to this. We've got we're in some level set, and regular level set, and it contains and inside M we have a sphere of dimension, say k-1. There's a k handle canceling a k-1. So the attaching sphere for a k handle is going to be embedded in M. And we have an ascending, so this is the descending sphere for the next k critical point. The ascending sphere for a k-1 critical point is going to be S. Okay, it's ascending, so it's n minus k-1 minus 1, right? Right, because I've got a k-1 critical point, it's ascending ball, it's ascending manifold, it's n minus k-1, and I'm intersecting a level set, which of course is just n minus k. K. Also embedded into n, right? And then we look at we have two intersection points between them. So let's call this, we'll just call this D for ascending, right? And then D intersecting with A contains 2 points, say P minus and P plus, right? And which are, they actually are as oriented intersection points, they appear with opposite signs, right? And we want to, the goal is to isotope D to eliminate. Isotope D in M. So D in M. To eliminate these two. Okay, that's what I mean by geometrically cancel. Because each point, those 2 points, correspond to flow lines from one critical point to another, right? And we want to get rid of those. And so we'll finish it off. If you can do that, then we're done with it there. Okay? And remember that m is dimension n-1. Okay. And so the picture you want to draw. Well, so what you need to do is you need a loop, and you need to use pi1 equals 0, and you need to get a disk, right? And then you want to do something along that disk. The disk has to be embedded. So I'll just tell you. So you're going to get a loop, gamma, which is going to it goes from say p plus to p minus in in say A, and then back in. So you choose some arc. So you've got two spheres intersecting at 2 points, and you choose an arc from those two. You choose an arc in each sphere connecting those 2 points, and that gives you a loop. And what you want then is that loop. So this loop of gamma bounds. What you want is gamma to bound an embedded disk in m minus a d. Well, except on the boundary, right? And so then you're going to get some picture dimensions sort of like this. You have this is an ascending thing, and then this is going to be your loop gamma. There's p plus, there's p minus. Here's your arc in one of them. Here's the it's hard to have enough dimensions to draw a picture, but this is a d. This is the loop gamma. It's going to bound a disk, and then you're going to mod. Actually, isotopy d is the same as isotopy a. Either one doesn't matter. And then you're going to actually isotope in a neighborhood of a disk and actually push it. So we're going to construct a really careful model of how this isotopy works. It's actually going to push A up and over this embedded D looks like a disk. D is this descending thing, and there's another disk. And so we'll do that next time. John can cancel those.
So because you're being careful here, you're not like introducing more.
We want to make sure we don't introduce more critical points. We do also want to, we want to make sure that I can actually talk. This is high dimensions, right? What does it really mean to push something along a disk? That's sort of easy, right? Worth writing. Good.